well known in the world because of their excellence in mathematics. And this is the reason why Airbus decided to collaborate with that institute back in the days where when they were starting to deploy in offshore countries. We still have this historical organization since the early days with two main offices, the headquarters in Toulouse, south of France, and the development center in Moscow, Russia. So the setup has not changed. We are since then, and after several years of management by Airbus, we became totally independent. So we are today a totally independent software editor. Working with all industries and having a worldwide deployment. So we distribute our solution worldwide thanks to a network of distributors. As I said, we have spread our footprint in many different industries. So despite the fact we come from aerospace, we have quickly evolved towards automotive, continuous manufacturing, naval industry, or chemical industry. So you have here a few references. It's just a subset, as you can imagine. But this variety of logos just show that the technology works in pretty much any industry. The software is all about mathematics, algorithms, machine learning, optimization. So it pretty much works in any engineering environment as long as you have do we have connection issues? Please let me know. So as long as we have simulation environment or pure engineering data available and not a massive amount, just a little bit of a small amount of data, we are relevant and we can bring value. The technology has been quickly deployed within Airbus, as you can imagine, first, and it resulted in a press release from the mother company back in 2013 with quite impressive gains, especially in performance. So 5% performance on a family of aircraft in the conceptual phase of the program, and also 20% design time reduction, so cycle reduction, which is absolutely huge, thanks to the deployment of our technology within the group in various departments. Meanwhile, as I said, we expanded in other industries. So I just wanted to share with you some successes that we had with, for example, Japanese automotive companies. So we have many references there. One of them being Mitsubishi Motors, where our predictive modeling technology, for example, allow them to build some predictive models for combustion engines and export them into neutral formats so that these mathematical objects representing the combustion engine is then subsequently used in 0D, 1D simulation environment, so multidisciplinary environment for acoustic simulation. It was the use case. We've done that because pSeven indeed allow you to export in neutral format, neutral as FMI, for example, or an Excel sheet or C program. Another nice use case in automotive is a well-known, let's say, and challenging benchmark called MOPTA 08. I think it was invented by General Motors back in the days in some US universities. The challenge here is to tackle very high dimensionality optimization problem with more than 100 variables, 68 inequality constraints, but within a given budget. And the budget, considering the dimensionality of the problem here, it was crash simulation, is very small. You see, it's less than 2,000 points for such an amount of variable. It's definitely small. But thanks to our technology, we were able to tackle that problem and actually find the optimum value in an amount of point which is actually less than this total budget. So with 1,600 or something iterations, we can get to the optimum. That was a nice success. So let me speak about the technology itself and what is different with our solution. So we fit in the fourth era of So this is the era of cyber physical systems. In that era, you need to provide, let's say, software technology enabling, for example, the collection of data from an assembly line, for example, or a system in operation. Then check that data against predictive models and potentially take some corrective actions if something goes wrong, or to enhance the performance of the system. So you have software discussing with hardware, and all of that managed by algorithms and artificial intelligence, for example. So this is where we fit. So if you think about all these buzzwords that you have on the screen right now, like machine learning, predictive analytics, or even MBSE, they actually all refer to the same thing, the same concept, which is what we call smart model. You can also call them a predictive model or meta model. These are actually very light mathematical objects, mathematical models, which work as a function. So you provide some inputs and it gives you some output, but it does it in a fraction of a second. And this is the benefit. Of course, the speed of these models is so high that you can then, by substituting a heavy model with this, you can then accelerate your design process. So these models are of course the know-how in the company, and we know how to build some very high quality models, let's say, so with a level of fidelity which is very, very close to what you can get using a 3D simulation or even test. So these models are built, as you can imagine, from data and using machine learning and artificial intelligence. The data set you can use might come from existing data, historical data, or you can, of course, generate your such a data set by running simulation. And for this, you need, of course, a workflow engine. So that is a good transition to the main capabilities of our technology. So we develop a product called pSeven. pSeven is an engineering process integration framework, which embeds also design space exploration capabilities and machine learning capabilities. So the main pillars are these ones. So you have a workflow engine enabling the capture of any engineering workflow. It has to be very flexible, as you can imagine, so that you can capture any workflow, whatever the software, the zoo of software that you might need. Then we provide design of experiment capabilities. So how to change all the parameters of the system and assess various combination of these parameters in an efficient way to minimize the number of evaluations, so that in the next step, using machine learning techniques, we can produce some predictive models. And these predictive models can be inserted into the design process, which can be more global. In that design process, you might find then optimization capabilities. So this is, we are very strong. We provide optimizers that can reach to or find the local, the global minima with a very limited number of evaluation. And so, because in some cases they are extremely expensive and you cannot afford having thousands and thousands of simulations. We also provide uncertainty quantification capabilities, so that allows you to introduce some variability or uncertainty in your system and observe the propagation of that uncertainty and what is the effect on the key performance criteria of your system, so that you can better control it and potentially optimize. Talking about the production, the product line. So we started with algorithms. So our roots are pure mathematics and algorithms. So the first product that was on the shelf was pSeven Core. So this is a Python library. Then 2 years after that, we released the framework. So this is a graphical environment. You will see it today, where you can capture your engineering workflow and run all these algorithms. And finally, last year, so this is quite recent event. So we have released this cloud solution now called pSeven Enterprise. So pSeven Enterprise is a brand new and native cloud architecture, which is derived, as you can imagine, from pSeven. allow, let's say, collaborative work. I'll come back on this in the next slide. So this is what the pSeven looks like. The desktop version, at least, looks like this. You see here a typical workflow captured by the user, and this one combines, let's say, a CAD update with some simulation. Here it's maybe Adams. We have CFD simultaneously running. So this is really multidisciplinary, complex multidisciplinary workflow. And all of that is actually feeding an optimization block here. So the optimization block will take all the information coming from the various disciplines and of course search for the minimum for a given of a given target. You see another branch here going to the optimization block. This is a pure machine learning branch. So from experimental data, we train a model, and that model, this smart model I mentioned before, is actually executed in various configurations, and then it feeds the optimization block. So actually, the optimization block drives this the execution of the model. And at the end, we get an optimum, and we export the results in an Excel sheet. So this is a typical engineering workflow and what you can do in pSeven. As I said, we have since last year this now extension of the technology to the cloud, and this is absolutely unique on the market. We have a native cloud solution here to not only execute workflows or to run some design space exploration task, but also to build the entire strategy and the entire workflow. So this is an authoring and collaborative authoring environment. So it works like Google Doc or Google Sheets. So you might have several users actually connected simultaneously to the same workflow and working together. So it extends the pSeven desktop application in various ways. Collaborative aspects, of course, is the main one. But because of the architecture and the nature of the architecture here, the users can, for example, run many workflows simultaneously. So all the workflows are delegated to the server, which runs in the back. The other beauty of the system is that once a workflow here representing a given strategy or methodology has been captured in the system, in the cloud, then you can publish it as a basic app, which go then in a specific area of the system called Apps Hub. So Apps Hub is a library of small apps which actually run workflows in the back, but the end user, doesn't see the complexity of the workflow here. Last but not least, of course, all of that is running in the cloud, and you don't need to install any software on the user machine. All you need is a web browser. The technology at under the hood, as you can imagine, is extremely complex, and this is one of the typical obstacle of all the solutions that you can find on the market, which is about the selection of algorithms, for example, and how to tune it. We have overcome this issue by developing something which is quite unique and called smart selection. So smart selection is an algorithm layer that comes on top of all the other algorithms that we provide in the platform. So whether you are doing approximation, so machine learning or optimization or simple DOE, that smart selection layer will actually do the selection of algorithms and the tuning for you, and in a dynamic fashion. So you don't, if you are a new non-expert users, let's say in that area, then you can fully rely on that technology to do the selection and the tuning for you. So of course there is an overhead, but at least you are sure that you can go through all the steps in an optimization or predictive modeling strategy. pSeven is a quite modern interface, so it's extremely powerful workflow engine. And this is what it looks like. So if you use it just as to run, let's say, a workflow, it's extremely easy to run. You just have to provide inputs here, and you will get some outputs there. So the workflow engine is something which actually not just run external application. It's more than that. It's actually run applications in a distributed environment and in heterogeneous IT environment. So there is a lot of work behind in the back to synchronize applications, to move files to the right machines, sometimes run on a cluster, sometimes runs on a local user PC, sometimes run on a workstation. And we have to adapt to the zoo of software that might exist in any engineering environment. So today, we will focus on Adams. But the type of application we can integrate is vast. We also have a user block concept, which allow you to define your own block that will go then to the library of blocks. If this is a typical software, let's say in-house development maybe, or external software that you use very often, then you can have it in your library, and all the users will benefit from that block. And can then build their workflow based on that application. So today, and before I pass the ball to my colleague Anton, I just wanted to introduce the use case. So in the features and functions I have described before, you will see first how we can integrate an application like Adams into a pSeven workflow. So more precisely, it's Adams car. Into a pSeven workflow. Then you will discover how we can set up an adaptive design of experiment strategy. And finally, you will see how we use surrogate-based optimization, so known as SBO indeed, to accelerate the optimization process for heavy simulation. So Adams is a fast and efficient product, but you can extrapolate that to finite element, for example, which can take hours before you get a result. And this is where SBO is extremely powerful, because you can get to the optimum value in a very limited amount of runs and iterations. So that concludes my intro. Thanks for listening, and then I pass the ball back to Emant or Anton. Let me know.
Yes, thanks, Laurent. Thanks for the great overview, Antoine. I've unmuted you, so you can speak now, and I turned off your camera, Antoine. So if you want to turn it on, you might want to do that right now.
Thank you. Yes, that's Anton Sartov here, and try to turn my camera on. And I would like to share, if possible.
Sure.
Yeah, thank you, Laurent, for this introduction. In fact, all the general aspects are now covered, I believe, and I can focus more on the details of this study, which we want to present here today to illustrate how pSeven can work together with Adams to solve the optimization problems. So the contents, the outline is the following. I will briefly introduce the customer behind this project, then describe the use case and the main goals of the use case. Then we will briefly cover the simulation model in Adams car and how we introduce parameters for our further study to describe the variable damping. And then we will switch to more practical part with the live demo on how the automated workflow for single simulation works in pSeven, how we then apply design space exploration capabilities on top of this single simulation workflow, and what results we get for our optimization problem. And we will finish with conclusions. So the project I will present today is the public version of the, I can imagine, bigger project with the NAMI, which is a Central Scientific Research Institute in Russia for automotive industry. They cover all main areas of engineering services, starting from engines through bodies, transmissions, chassis, and even electronics and internal conditioning and accessories. NAMI intensively uses the simulations in their design processes and consulting, starting from 1D modeling for system level design, model-based system engineering, of course, finite element methods for crash tests, for stress analysis in general, and CFD methods for aerodynamics. And in this environment, our product finds its place as the platform to automate some of the simulations and unify them into single workflows. I will skip this slide because I believe most of the participants are familiar with Adams and what it can do, and switch to the actual goal of the whole project and objectives we wanted to reach. And the goal is not only to solve the optimization problem, well, indeed, that's of course the most practically interesting outcome, but also to create an automated suite for parametric analysis of the car suspension to ensure the passenger vibration comfort under different vehicle behavior for different roads, profiles, and therefore to simplify everyday exploration of such problems. So to reach that, we need to integrate the Adams car model into pSeven workflow and ensure that we can do flexible simulation setup for different driving conditions. Then we need to apply design space exploration for our parameters of variable damping for front and rear suspension, introduce some responses we want to measure, which will represent the passenger's comfort, and as a final task, to address the single and multi-objective optimization problems and in fact identify the best combination of those damping parameters. The model here is, well, for public purposes, based on the standard model from Adams database. We consider two driving modes. One is the full road, where we provide the full profile of the road, incorporating, well, the statistically meaningful obstacles and road behavior, and the single obstacle case when we consider a particular fixed obstacle on the road, and therefore we can focus more on the detailed behavior for a particular case. These two cases address two main investigation scenarios. So basic study of the damping for fixed conditions and, let's say, average performance for some representative road profile. We will see later on that we can combine those scenarios in the form of the workflow, and this is one of the goals of the project, to enable this smooth and simple switching between different studies. Outputs. We want to investigate the passenger vibration comfort, and there are a lot of formulations in the literature and based on different expert knowledge how we can actually define those responses. In our automated workflow, we of course will obtain the outputs from Adams, which are displacements, acceleration, forces, distributions of energy densities, whatever things which we can extract from our Adams model. And on top of that, we need to somehow define what we call passenger comfort. Again, variety of options exist, but we focused on several pretty, at least for in this demo and this public version, several obvious things. We consider angular movement and acceleration, so pitch, also roll, and the vertical movement of the chassis altogether. And we consider the root mean squared of these values over the time period which we consider. So over our driving period, we actually simulate. That's what we will use in most in our studies. There are other outputs which are also, let's say, monitored, so saved for additional analysis if you want. And for each characteristics, we also perform transformation to the frequency domain, and therefore we can analyze the amplitudes in the frequency domain, which opens the door for more sophisticated formulations of the problem, where we actually narrow the range of frequencies where we're looking into our responses. Then the variable damping. So we introduced the variable damping coefficients as a piecewise linear curve. So we describe the dependence of the reaction force for compression and rebound as a function of the stroke speed. You can see in the plot that we have a piecewise thing where we introduce parameters for the slope for rebound, slope for compression, the point of inflection of this linear curve, and the maximum forces on both sides, which leads to 12 parameters in total. Why to stay with this parameterization? From one point of view, it's simple enough to be clear for everyone. On the other hand, it can provide really different shapes of our curve, thanks to the fact we don't consider it as symmetric, so we consider different slopes for compression and rebound. And can also imagine that it can be extended to be even more, let's say, non-linear, approaching the full spline concept, where we control more control points in our curve. One comment, I won't dive deep here, but of course, when we introduce our parameters as independent features of the curve, we can get many different curves shapes. However, we have bounding lines which are coming from the well, technological feasibility, and we don't want to violate those bounds, and we also cannot afford to have the slope of the second line of this segment to be negative. This all will be represented as constraints for our parameters combinations, which we will need to satisfy. Okay, that was the intro of the model. Now we need to actually switch to the study. What steps we need to perform to solve optimization problem in pretty generic case? First of all, of course, we need to automate our simulation and obtain our automated source of responses to analyze them in an iterative way with different parametric study methods, design-space exploration methods. Then we need to perform a basic parametric study just to ensure that our model is stable enough, that it behaves as we want, to investigate the basic dependencies, maybe reveal some important features that will help us to finalize our optimization problem statement and solve the problem we actually should consider. And in the end, we switch to optimization, where we have our targets to be improved, and we're actually looking for the best configuration. I will skip this part about the workflow basis. Laurent covered that in his introduction, and I will just show you the workflow in general and switch to the live demo. So again, as the main comment, probably I will switch it now. It will do. Yeah, so now I'm in pSeven. Somewhere in the background, I have my Adams model and all associated files I need to modify in order to set up my simulation. Here we utilize the Adams in a batch mode. So we have the program block here in the center, which actually launched the Adams simulation from command line. And in order to do that, we need to update the solver session file, where we change the road settings, the speed, the solver settings if we need to tune something. And we also need, of course, to update the definition of our damping coefficients based on the parameters we introduce as users. This is a workflow for single run. So we actually should type in or provide with the copy paste some parameters of our damping curve. And in the end, we will get our responses. In this place, I can edit my workflow. This is just a capture of the flow, and the links represent the data transfer and files transfer. And if I switch to Run tab, I can actually see my inputs where I can modify them, and the outputs I will need to get. I will probably modify something now. It's the maximum force. Again, it may be copy paste, or here I will do it manually for these two values. And once I produced or provided all the inputs for my damping curve parameters, I can run the simulation. And you will see that it just starts the executing blocks. They are flashing. It means that their step is going on. We update our files, and we actually run the Adams solver in the background. It will take us some time. What else do we have here? We have this part where I have parameters. Those are not the definition of our damping curve. Those are more the settings of our study, including the path to the Adams if I want to transfer the project to another machine. I have the road type, where I can switch by number between different road profiles. Therefore, I cannot even go to Adams anymore if I want to study different combinations of my road types and velocity of the vehicle. And well, it's finished, and now at the right I have my results. Of course, that's just numerical things, and it's not very convenient to check, but I can switch to the last tab in pSeven, which is Analyze, where I have presets of my results. Again, since it's a single run, what I have a plot of my actual damping curve for given parameters I specified, and the outputs. in the form of the plots as a function of time, and I can see how my pitch, roll, and the vertical displacement evolves during my ride. And also in orange, I can see the same outputs in the frequency domain after Fourier transform. So if I want to identify the particular frequency range and see what the amplitude, I can do it. And more viewers are available, in fact, for all of the outputs we consider. So already this single study, single run, is useful because you can change all settings you actually promoted to be available here in the workflow, not actually changing the model in visual way, and perform fast checks for different assumptions you have, let's say, in manual mode. However, of course, this workflow for us will be a basic brick for for further study, which is design space exploration and optimization on top. So now we have our block, which gets our inputs, which we want to change and search for the optimum configuration, and provides the outputs we actually want to analyze. So next step, design space exploration. This is a general concept. First of all, we will perform design of experiments, which is, well, in simple words, a uniform sampling in our ranges for variables, for parameters, in order to investigate how our responses behave, measure the sensitivity of the outputs with respect to the variation of inputs, and in general, let's say, estimate our model behavior, get insights for the optimization problem statement, and even reuse the data we will get during this step for surrogate-based optimization as initial sample. pSeven provides many DOE techniques, and we have smart selection, as Laurent mentioned, to choose the most appropriate for the particular problem. Again, I will probably switch directly to the live demo and show you how the workflow for the parametric studies look like. And this is here. So what do we see on this screen? We see blocks, which are in fact folders. If I go inside this folder block, I will see immediately the same workflow we just checked. So we used the workflow for single run as the basic block for our cycle study, which is in this case DOE, which provides point by point and gathers responses from our model. There is another block also here. It's called quadratic, and this represents the function which allow us to evaluate constraints which I mentioned. Those are, let's say, auxiliary comparing to the simulation, but really important because we want to have only the curves for damping which satisfy our requirements for technological which can be reproduced by technology. And it's all governed by this design space exploration block. And if I open it, I will see the main settings. So what do I have here? I have the list of parameters I want to check, to change. I have the bounds for those parameters, lower, upper, and those are parameters describing my curve. They are considered as independent, as typical for any parametric study. They all continuous. And here on the bottom list, I have all the outputs I produce from my model by changing, calculating the sigmas and frequency domain sigmas, and they all have type evaluation. That means I only need to collect them and explore how they scatter in my design space. However, here I have the first line, this quadratic constraint. So in order to ensure it will satisfy for my design of experiment, I will just switch it to constraint. And you may notice that the technique for the whole study now changed to adaptive design. That's how smart selection works. You specify your problem, you specify what you want to do with your outputs, and you get the proper technique, which will be then tuned during the run, also automatically. That's it for the settings for adaptive design, where we will investigate and study only the configurations, combinations of parameters, which satisfy our constraint for curve shapes. In the analyze for this case, we have For example, the scatter plot and the correlation plot. Here I have only some of the outputs plotted, one versus another. So I can see, for example, that here in the selected plot, the acceleration for the roll and the acceleration for the vertical displacement are competitive functions. So for our study, we need to reduce both of them, but we cannot go actually to this corner and we see that there is a boundary. This is nice candidates to be competitive target functions for our optimization, because here we see that there is a the problem that we cannot evolve them altogether, which is not the case, for example, here, where we see that they evolve in sync. So reducing the one, we can reduce another. That can be complemented by more formal values of correlation coefficients, which show us that actually, yeah, these guys have pretty strong negative correlation, which means that they will evolve in different directions if we will change parameters. We can also, for design of experiments, check the visual part in parallel coordinates, and maybe filter some of the ranges and see how it affects on our scatters. And one more thing we can check is the dependency analysis, where we consider a particular output and we see how it's affected by the changes in different inputs. And we see, for example, that the slope of the first segment for the compression is the most important for the vertical displacement acceleration. And that may be also an insight for us which parameters we can remove from consideration and which we should consider with more details. Now we need to switch to optimization study, because we know now more about our model behavior. We have everything ready. And just to remind you for what we have again a lot of optimization techniques in pSeven. We have smart selection, which will help us to choose the algorithm automatically. We have 12 parameters describing our damping curve. We have quadratic constraints to ensure that we don't violate the boundaries for this curve. And we have two criteria for optimization, two target functions, which is the vertical direction acceleration and the acceleration around of the rotation in the roll. It will be two independent objectives for optimization. Therefore, we will get a Pareto frontier of the results of the answers to be explored to choose the most appropriate one for our needs. Switching back to pSeven, how we will actually set it up in our block. Going back to edit, I will use the same workflow, same block, and actually all I need to do, I need to go and find my sigma vertical displacement, sorry, where it is. Yeah, sigma roll. It will be my target for minimization, and sigma vertical displacement also my target for minimization. I can add more targets, but it will be even multi-objective optimization study, which will be harder to analyze in terms of results. Or I can keep only one target, and it will be effectively single optimization problem. Thanks to the fact I promoted all of the outputs I actually measure to this list, I can play around with the settings and actually study different problems with a couple of clicks and some time for actual evaluation of the problem. So now I have my optimization setup ready with 2 clicks. I can run it. Well, it will take hours, so I will immediately switch to the existing report for optimization. Again, as I mentioned, this is a 2-objective optimization study. I have my acceleration roll and acceleration for vertical displacement outputs as a competitive ones. We want to reach this corner where all responses are as low as possible, and we have a boundary which prevents us from going there. This is a Pareto frontier of competitive optimum results, and we can explore what we have. And by pointing out or just selecting, we can actually see which pictures it goes. So if I change it, it will redraw the actual plots. My laptop, it's a bit smaller than it was expected, but it's like a dashboard where we can actually analyze your result. And again, as for single simulation, when you rerun your problem, you just update this report, and it automatically will grab the new results and show you the new Pareto frontier, and you can see what you get for new cases. Colors here shows the sample obtained on DOE stage, so we also utilize that as an initial sample, and you can see that the actual optimization with the red points kind of shifted the cloud of orange points towards our not reachable ideal point, and we actually have a boundary here in the end, which is the candidates for us to choose based on our feeding or expert knowledge or expectations. So those are our results, and to comment more on those, I will switch again to slides and comment first on the technique. So we applied, well, automatically selected by pSeven, surrogate-based optimization technique. This is a global technique, which is more important for us in this case than the fact that it's an evaluation saving, because simulation in Adams, as you noticed, took us about, well, a minute. So we can allow to do multiple runs. However, we want to make a global exploration, and that's another benefit of SBO, is by nature a global method. We discovered the 36 Pareto frontier competitive points within 600 iterations, which is, well, much less than you can expect from well-known gradient-based or even non-gradient methods. And the overall computational time took here about 10 hours. Should be, yeah, about 10 hours, which in fact was one of the goals of the whole story, to enable these studies to be performed overnight. So imagine in the end of the day, you formulate some assumptions, you run the simulation, the optimization campaign, and in the morning you get a report which you need just to update and actually investigate what's going on. So thanks to SBO, it was possible. Some pictures of the points on the Pareto frontier, where, well, you can imagine that they provide damping behavior and in different points, and you can actually choose, do you want to go to one extreme, to another extreme, or stay somewhere in the middle. And the last picture is here. That was I was missing on my plots in pSeven, the initial configuration. Definitely it was not ideal, but you can see it somewhere in the middle of the whole cloud of points. So, well, it was not the worst. It was somewhere, well, reasonably close to Pareto frontier. But after our study, we automatically get all the points which are better than our initial configuration. And if we will consider the initial configuration with this particular point on Pareto frontier, we will see that we gain about 10% reduction in the angular acceleration for the roll. For vertical displacement acceleration, we reduced by 10%, and angular roll acceleration reduced by 2%. But that's, of course, for this particular point on Pareto frontier, which is a nice result, considering the fact that the initial configuration was not really bad. That's how you can utilize pSeven for both automating the, let's go to conclusions. Yeah, so we integrated the Adams car and pSeven platform together in order to automate the studies on top of the Adams car model for a particular problem of exploring variable damping parameters to ensure the passenger comfort. This automated workflows allows now to easily extend the simulation scenarios, switch between them, and compare, carry many studies with a unified methodology. So it's a step forward, let's say, to the fully automated suite, where you have all basic parameters promoted to the final user. We solved the two criteria optimization problem for the variable damping characteristics for front and rear suspension, with the targets of minimization fluctuations in acceleration for the roll and for the vertical displacement, obtain the Pareto frontier, which is a tool by itself to explore what we have in terms of potential options. We compared the results with the initial configuration we have, and thanks to SBO technique in pSeven, the optimal solution was obtained with a minimum number of model evaluations, which again enables the fast exploration of different problem statements with the reasonable evaluation time. Thank you for your attention, and I hope we have 5 minutes, for questions.
Yes, yes. Thanks, Arthur. So there's a great presentation, great demo, very thorough. So thanks. It's very interesting. Thank you. So at this point, I want to shift the focus to some questions and maybe a live interaction between the presenters and the audience. So if you have any questions, any feedback on the presentation material so far, either on Data Advanced or pSeven, or the integration with add-ins, please ask away in the Q&A window or the chat window. There are a couple of questions, Laura and Atwa, that I've received. The first one is about the meta model that you mentioned. The question is, can the meta model be exported? And I'm guessing the user wants to export it out and use it outside pSeven. Is that possible?
Yes. Yes, it's absolutely possible. So when you have built a model within pSeven, you can export it outside of pSeven in neutral formats. So there are several formats supported, and all of them they will allow you to run the model without pSeven, so without the need of any license. These formats are C in compiled way, so C executable or C source that you can then compile, C#, Octave, MATLAB, Excel sheets. So you can also have a very complex Gaussian processes model captured in an Excel sheet with attached DLLs. So there is a macro, of course, running in the back, but it's an Excel sheet you can also run. And you can export also in FMI, FMU format. So that's the case I had mentioned in the intro for Mitsubishi. They use that format, because it's quite popular in systems engineering. So yeah.
Okay. Okay, perfect. There's another question that I've received. The question is, can you use pSeven to calibrate time-based responses? So I'm guessing the user wants to take an output that varies in time and perhaps calibrate some of his model parameters to align with that response. I can clarify what exactly this means, but does that help? Can you guys calibrate to a time-based response? Okay.
Yeah, let's consider, for example, this example which we have. Imagine I have this roll response in time, which is in fact the time-dependent response from Adam's simulation, and more or less almost all of the responses from Adam's simulations will be time-dependent functions. And if I have a curve which I want to match, yeah, actually I can do it. So I can actually take this plot and add, in terms of workflow, another block which will compare the target curve, my actually generated curve, to form the target to minimize, so the definition of difference between those two curves. And then the rest will be almost the same. So we'll run this Adam simulation, get our time-dependent curve for a particular set of parameters, compare it with the target one, return to optimizer the difference, and it will try to minimize it, which will be the match. I especially pointed out that there will be a block which will calculate this difference between. Typically for real life problems, we should be careful in the way how we define this difference. So it may be many cases it will be a standard least squared formula, but sometimes we need to address particular parts of the curve with more accuracy, or incorporate the knowledge on the errors in particular measured points. But yeah, indeed, this is one of the scenarios, and definitely there's an optimization problem.
Okay, perfect. Thanks, Antoine. There's a question about differentiators. So there's a specific tool that is mentioned here. I won't use that, but can you just broadly talk about your differentiators as against other tools, other solutions provided for design optimization?
Yeah, I can give a quick picture here. So yes, there are definitely differentiators. First of all, that advanced company has been created again back in 2010. So at that time, even on that year, many equivalent solutions were existing on the market. So the pioneers in that business area emerged at the end of the 90s, just to give you an idea. So when the company was created, there were very, let's say, mature solution already existing on the market. So the question is good, actually. Why would an Airbus company create another tool to address the same things? Well, the answer is very simple. In many different, let's say, advanced industries, you really need some extremely powerful algorithms to tackle extremely highly nonlinear problems. It's the case for CFD simulations, so aerodynamics of an aircraft, for example, or other nonlinear behavior. And the solutions that were existing on the market at that time, which are still there, actually were not giving satisfaction to the aircraft manufacturer. So this is why how the story began, to bring to the market, let's say, a new generation algorithm that surpasses, let's say, what was existing at that time. So we still have that key differentiator. So all the algorithms that we develop are built in-house. So we master really the mathematics at the back. So of course we have not reinvented the wheels. When something was already existing, we of course started from there, or we were very inspired by competitive solutions. But we have built our entire suite of algorithms, from DOE to optimization to predictive modeling, to tackle these very specific nonlinear problems. So the differentiator is first the performance, of course, of these algorithms. It's very difficult to assess. I agree. You have to do a benchmark for this, and we are happy to run it if necessary. Another aspect which is a clear differentiator is this smart selection. You will not find that in competitive products, which at least covers all aspects of design space exploration, from DOE to optimization to machine learning, etc. So predictive analytics. We are the only one providing such technology on the full scope of design space exploration capabilities. Finally, there are many more differentiators, but I would like to mention a last one. This is the native cloud solution. We are the ones who first started to develop, even in 2010, a process integration framework with design space exploration capability using web technology. So even the first version of pSeven is actually based on web technology. You don't even realize it when you open pSeven because it's a desktop application, but it's actually all web stuff in the back, which allowed us then a few years later to go full native cloud solution. So today we are the only one, let's say, providing a full native cloud solution, from authoring. I insist on that because this is a key differentiator, from authoring to running to post-processing to publishing into small apps. This is absolutely unique. You have other web, let's say, solutions on the market that sit on top of existing platforms like pSeven, but you cannot necessarily build the workflow in a collaborative manner using that technology. So this is a key differentiator.
Okay, all right. Thanks, Martin. This is very thorough, nicely explained. So at this point, we are running a little over. There are a couple of other questions, so I'll try to get that addressed by Lauren and Antoine online and have those answered. With that said, thanks to the participants speakers from Data Advance for going through the pSeven Airbus integration. Thanks, Antoine. Thanks, Laurent, very much for the great presentation. A recording of this particular webinar available for viewing later on. And if you have any questions about either of the two technologies, either Airbus or pSeven, please reach out to us, and we'll get you connected to the right people. With that said, thanks again, and have a good rest of the day, everyone.
Many thanks, Hemant, for organizing this, and have a good day, everyone. Bye-bye.
Thank you. Goodbye.